This is a report on integrated circuits with Dr. Jim Angel, Professor of Electrical Engineering and Director of the Solid State Electronics Laboratory at Stanford University, and Dr. Harry Sello, Manager of the Materials and Processes Department at Fairchild Semiconductor Research Laboratories.
Hello. We're here to tell you about a recent revolution in electronics. Of course, there have been many recent revolutions in electronics. You hear about them all the time. We'll tell you what is an integrated circuit, how to design it. We'll go through the agonies of how it's made, and finally, tell you about some of the uses of it and what they're good for. But first, let's have a commercial.
It started here. Pure PN junctions from a pile of sand. Planar silicon integrated circuits. Invented here. The epitaxial process, a secret locked in a crystal. Higher yields in 1/10 the time. Invented here. Metal over oxide. You can't make an integrated circuit without it. Invented here. Fairchild brought out the first NPN silicon mesa double diffuse transistor, the first PNP silicon mesa double diffuse transistor, the first planar NPN transistor, the first planar PNP transistor, the first lifetime controlled silicon planar transistor, the first planar epitaxial PNP transistor, the first silicon RF transistor, the first planar 2 transistor, the first planar silicon controlled rectifier, the first planar epitaxial power transistor, the first resistor transistor logic family, the first complementary transistor logic family, the first dual inline package, the first commercially available face-down bonded circuit. Processes, product, packages, price. Oh yes, and production. Invented here.
Let's get started, Jim, by you saying what is an integrated circuit.
Here is a packaged integrated circuit. Inside this package is a chip of silicon which provides the electrical equivalent of many transistors, resistors, and diodes, all interconnected to provide the desired function. Before we discuss in detail what's inside that package, I'd like to show you some evolutionary examples of what integrated circuits can do for the appearance of electronic equipment. Here is a photograph of a printed circuit board from a digital computer a la 1960.
Prehistoric.
Right. Built out of transistors, separate resistors, and diodes, wired together on the printed circuit board. Here is the electrical equivalent of the circuit you saw in the previous photograph, built in integrated circuit form of vintage 1963. Notice how much smaller and simpler this board is. I have here a newer version of integrated circuits containing in the upper left-hand corner 8 integrated circuits outlined. Now those 8 integrated circuits provide essentially the same function that was provided by this board, namely 24 integrated circuits down to 8. Notice that the wiring on this package is extremely orderly and well organized.
I see less pin connections, too.
This is perhaps typical, Harry, that we find as we make a more complex function in one structure, the number of pins tends to go up only as roughly the square root of the complexity that's provided by that board. Now you've seen an evolution of transistors to early integrated circuits to modern ones. Let me show you a series of photographs which shows you what's inside the corresponding cans. Here is a photograph of a single transistor chip, such as we might find in the 1960 version of the computer board I showed you.
Old style again.
Here's the intermediate style. You remember the 1963 integrated circuit packages. Here's what would be in one of them, typically 10 transistors. Here is a modern 1966 version of integrated circuits with many hundreds of components on this one circuit. This particular function provides 16 bits of digital memory in this one package. Now, integrated circuits can not only be used for digital, but also for linear service. Here is an IF strip, transistorized and hence perhaps 3 years old. Here is its integrated circuit counterpart, providing exactly the same function. Notice how much simpler it is. The wiring is roughly the same. the simplicity is greater. Hence, we can expect that it will not only be cheaper, but more reliable. And these are perhaps the most important contributions of integrated circuits.
Let's get on to how to design an integrated circuit.
All right? Let's do it by way of an example. Up here we have a circuit for a typical structure which might be in integrated form. This particular circuit has 20 components in it: diodes, transistors, and resistors. After the configuration has been chosen by usual techniques, the next step is to build a breadboard model in actual working form. On the breadboard, we have separate transistors and other components, all actually wired into a working circuit. The purpose of working with the breadboard is to try to optimize the numerical value of each of the components in the circuit. Once this optimization has been achieved, the next job is the design of the masks, which will be used to make the integrated circuit. Harry, I wonder if you could cover some of that work.
Yes, I can. So, we made the engineer pick up a soldering iron. Let's see if we can make an artist out of him by using yet another example. Here is a full-scale 30 by 30 inch piece of typical integrated circuit artwork, which represents in a careful, precise form the interconnection pattern of an integrated circuit. For example, these are the metal pads. These will be on the integrated circuit, the metal pads which connect to the outside world. Here we have the transistors. And here are diodes and more interconnecting metals. The problem here is to very carefully and precisely convert this large-scale drawing into a small, precise version of this on a 2 by 2 inch glass plate. This artwork is reduced 500 times by a process of high-resolution photography to a glass plate upon which the pattern shown by the artwork is successively stepped and exposed all the way across the glass up to 1,500 times, which means, of course, 1,500 integrated circuits. Now, the artwork which I showed was only one mask, potentially. Here is the artwork in reduced plastic overlay version, which goes with a complete set to make an integrated circuit. There are 5 to 7 or even more of these potential masks. All of these must align carefully and precisely. These then will be translated into another set of glass masks, which will then be used for contact printing directly onto silicon wafers. In working with silicon, this is what you begin with, a silicon ingot. It's a glass-like material, very brittle, very much like diamond. In fact, it costs about like diamond and is a member of the diamond family. This is made in a series of long rods by a process known as crystal pulling. It cools as it is pulled. However, it is still very hot since it's been grown at a very high temperature, up around the region of 1,400 degrees centigrade. We cut this into thin wafers, about 12 thousandths of an inch thick, by using a diamond saw. After cutting, the wafers are very carefully polished, so you end up with a mirror-like surface, which is essential in the preparation of the integrated circuits. The finished chip is about 5 thousandths of an inch thick.
Let's take a look inside the silicon. This is a cross-section of the wafer we've just watched being made. To protect it from the outside world, we allow oxygen to react with the top surface and grow an oxide called the passivating silicon dioxide layer. Now we're going to make use of the masks we made earlier. First, the wafer is coated with a photosensitive resin. The mask is then placed on the wafer, and the system is then exposed to light. As a result, the exposed resin hardens. The remaining resin can be simply rinsed away. The wafer is then exposed to acid. Those areas of the passivating layer not protected by the hardened resin are etched away. In the next operation, called diffusion, the wafer is exposed to a dopant. This impurity diffuses through the window and into the silicon below, forming the collector of a transistor in our integrated circuit. But notice, At the same time diffusion is taking place, more oxide is being formed. This is the essence of the planar process. Now we're going to strip off the passivating layer and grow a new layer of silicon right on top of the diffused wafer by a process called epitaxial growth. Now we form electrically isolated regions on the wafer by a process of diffusion, photosensitive coating, masking, exposure, rinsing, etching, and diffusion. Next, we prepare the individual parts of the integrated circuit. First, a transistor base and a resistor. The same procedure is followed. Notice that diffusion takes place not only downwards, but also laterally under the oxide. As a result, the junction is formed beneath the passivating layer, where it is protected from the outside world. The next diffusion forms an emitter and a collector contact to complete the transistor. Again, the same process. The next step enables us to interconnect the various components and to make contact with them. Again, we'll etch windows in the oxide. But instead of another diffusion, a layer of metal is deposited over the entire surface of the wafer. Then, by use of the proper masks, the excess metal can be etched away. Sometimes we like to make resistors a different way, by using the metal interconnection pattern. All you have to do is make the metal pathway a little narrower, and it provides higher resistance. If we wish to make a capacitor, we take advantage of the fact that the oxide layer is an excellent dielectric material. A small area of metal is deposited, forming one plate of a capacitor. The oxide is the dielectric, and the silicon directly below the oxide forms the other plate. The series of schematic operations taking place on one structure that you just saw actually takes place across a whole wafer. This results in a wafer containing many integrated circuits, up to 1,500 of them. Now comes the electrical testing of this wafer. Jim, can you take over on this part?
Certainly, Harry. Even though we have been very careful in fabricating this wafer containing many hundreds of integrated circuits, not all the circuits on the wafer are flawless. The first job is to determine and mark those circuits which are not good. We test the wafer in a probe testing machine. We then scribe the wafer using a diamond point in the scribing machine. After separating, cleaning, and drying the integrated circuits, we fish out the ones that are bad. If we have been successful to this point, we have a high yield of good ones. From this point on, we are going to package the circuits, and so whenever we throw one away, we're going to throw away a complete package.
That's a good point, Jim. Let's look into this matter of packaging a little bit. You know, we've exercised a lot of care in bringing the integrated circuit chip to this point in the processing, and we've also done it economically, because mostly we've processed them as wafers, 1,500 at a time. From here on out, as you pointed out, we will be handling them as individuals, putting expensive packages around them. So how we treat the packages is important. In the old days, it was simple. You had a wide choice, two, large and small. A TO18 outline, small, and the TO5 larger outline. These days, we have upwards of 250 varieties of packages, and a user can select any one of them. Here are an example of three of these. A dual inline package, a plastic package, and a flat pack. The most nearly universal of these is the dual inline package. Let's take a closer look at just how that is made. You start out with the idea that you're going to build a tasty but inedible sandwich. Here are the two halves that you begin with. Two ceramic parts into which the integrated circuit chip will form the sandwich meat. The two halves are glassed with a material which will form the solder that glues the two halves together later. A Kovar frame has been prepared in advance and cut out to the pattern necessary to connect the chip to the outside world. This Kovar frame will also be placed in the middle of the sandwich alongside of the chip. And here is the arrangement. Chip in center, Kovar frame around the outside, and notice that the tips of the frame here have been metallized. This will form the connection to the chip directly, as shown here, where the lead bond wires have been placed connecting the pads on the chip to the metallized tips of the Kovar frame. We complete the sandwich by putting the top half of the package right on top of the frame. The next operation will be to clip the ends of the frame. The package is now revealed in its magnificent beauty. The solder glass is peeping out, so that we have to clean that up a little bit by sending the part through the furnace along with many thousands of others, so that the solder glass is all melted in and neatly arranged in place. This is the finished dual inline package.
Now that the circuit has been packaged, we must again test it substantially before we would dare ship it to the user. First is a series of electrical tests, many of which use special test equipment, which is again built from integrated circuits. Many of the tests made on the integrated circuits now duplicate those tests which were made on the wafers. In addition to these tests, which duplicate those which were made before, we must make some special tests, such as frequency response of a linear amplifier or switching speed of a digital circuit, before we would dare ship the unit. We can't make these tests on the wafer state due to the limitations of the test equipment through the probes. In addition to these electrical tests, we make a variety of mechanical tests, such as shock, vibration, and acceleration. Finally, we make a set of temperature tests, running the unit at high temperature and at low temperature to ensure that the unit will work dependably in service.
Now let's look into some of the things that we can do with integrated circuits. But first, a commercial.
For the past year or so, Fairchild has been publishing a series of applications notes on integrated circuits. If you read the design journals, you might have seen one, if the guy ahead of you didn't tear it out. They talk about the switch to integrated circuits, how to design them in, when to use them, which ones, their costs, basic design rules, a pretty complete short course. Then, on the back of each sheet, we've covered a specific industrial application, an XY controller, a tape reader and display, a cycloconverter. A dozen ideas. But if you're really serious, you'll have to read the book. It covers all the IC families. Digital, linear, hybrid, memory, custom. It tells about packaging, testing, and of course, how to order ICs. Altogether, that's about 100 pages of fresh information on integrated circuits. We'll send it to you if you'll write us. Got a pencil? Fairchild TV Briefing, Box 1058, Mountain View, California. We'll send you the whole stack by return mail.
Now that we've talked about how to design, build, and test integrated circuits, let's look at some of the functions which are available now in integrated circuit form. Here is a list of readily available digital circuit functions. This list includes about all the circuits which are needed to build the electronics part of a digital computer. This list of linear functions includes a large variety of things. As you probably know, operational amplifiers, for example, are rather precise amplifiers that are used as the major building block of analog computers. The voltage comparator is a circuit which very accurately compares which of two voltages is the larger.
You know, it's exciting to think that all of these functions are here today. They can be used. They're available. And it's even more exciting when you consider the number of applications that these can be put to. You couldn't even begin to make a list of all of them. Actually, the uses of integrated circuits are limited only by those who are designing these uses. Let's take a deeper look into some of the present-day applications of integrated circuits.
One of the many industrial companies using integrated circuits today is Burroughs Corporation. At Burroughs, integrated circuits in dual inline packages are inserted in circuit boards automatically, affording more efficient production. Using this machine, which is proprietary with Burroughs, a single integrated circuit can be installed for about the same cost it previously took to install a discrete component. In order to automate the entire manufacturing process, Burroughs uses other advanced techniques such as flow soldering. This guarantees reliable connections to each integrated circuit. In addition, computerized wire wrapping machines are used to make the backplane interconnections so that the inherent reliability of the integrated design isn't compromised. The machine automatically cuts each wire to the correct length, strips the ends, routes the wires, and makes the connections. Meanwhile, each completed circuit board is tested individually. Finally, circuit boards are installed in the computer frame and the completed system is thoroughly tested. Burroughs is now committed to integrated circuits and, in fact, recently placed one of the largest single orders ever placed for these devices. For Burroughs, integrated circuits provide a significant cost reduction and a proven increase in reliability, both of which are real benefits to Burroughs customers. Stromberg Carlson is another company committed to integrated circuits. Their data products division is now manufacturing the first in a line of new Stromberg Carlson products built with ICs. Integrated circuits, in this case in TO5 packages, both metal and plastic, were used in the SC1100 because of their low cost, size, reliability, and, as Stromberg Carlson says, because integrated circuits are here to stay. The SC1100 system consists of up to 18 desktop interrogators like this one, which are handled by a single station control unit, which in turn ties into the computer memory. The operator asks the computer a coded question on the interrogator. The computer responds with the requested information almost instantly. For instance, with an employee personnel record. This is the Model 388 AM/FM stereo receiver built by H.H. Scott. It's only one of a new line of hi-fi components in which linear integrated circuits replace discrete transistors. Scott engineers have chosen ICs for one specific purpose: better performance. More stations can be pulled in with less noise and interference. Weak stations become loud and clear, and outside interference is drastically reduced. But there are other benefits too. A total of 37 discrete components in the receiver's IF strip have been replaced by only 4 ICs. This new approach to circuit design promises even more dramatic new products from the people at H.H. Scott. We've seen some examples of how industry is putting integrated circuits to work today. But how about the future?
Well, that's a very exciting part of the story. Research is constantly going on to find new ways to use integrated circuits. Not only in the R&D labs of semiconductor manufacturers, but in the universities, like here at the Solid State Electronics Laboratory of Stanford University in Palo Alto. The facilities you see here in this integrated circuits lab are made available by funds from many industrial organizations. Our lab at Stanford is a miniature of the production facilities you've seen in industry. It was built with the help of contributions from the majority of our nation's semiconductor manufacturers. Right now, we're working in several areas. We do basic research in integrated circuit technology. We're doing circuit research using the unique capabilities of integrated circuits. We also develop devices which incorporate ICs. And we conduct research in several peripheral areas. As an example of our research in IC technology, we're studying new ways for getting impurities into semiconductors. Normally, this is done by diffusion. We do the same thing by ion implantation. This machine takes individual ions and accelerates them, ramming them into semiconductor material much the same as you would shoot a bullet into a bale of hay. Right now, this is a much more expensive process than diffusion, but it's a different technique. Here, we're not interested so much in developing the technique as we are in learning the fundamentals. How heavily can you dope materials, and what kinds of materials can you dope this way? Let's look at an example in the field of medical electronics. Here we're using IC technology to develop an array of fine probes which a neurologist can implant down in a living brain to study the potential at different points on a single neuron. Here, you're looking at one of the masks prepared by the student doing this research. We're developing probes using the same technology as for the metallization patterns on ICs. The probes will probably be of gold. This would have been impossible before IC technology. One of the most dramatic devices being developed is this reading aid for the blind. This is a reading device in which ordinary printed material is converted to a tactile image which is presented by a closely spaced array of 48 piezoelectric reeds. By resting his finger on the vibrating reeds, the blind person can sense a vibrating and grainy facsimile of the material being viewed. The great advantage is that this machine enables a blind person to read the printed page. This version is relatively large, even though it incorporates integrated circuits. Ultimately, one 70 by 90 mil chip will take care of all the necessary electronics to drive one vibrating reed.
Certainly, integrated circuits are used in many present-day applications, but we mustn't forget one very important factor, and that is the reliability of an integrated circuit. It is a reliable device. In the industry, we've logged almost 80 million element hours without a failure. That's reliability.
We have considered many different things regarding integrated circuits. One question which we might ask is, why do people care about integrated circuits? Well, there are many reasons. Certainly one of them is the reliability factor that we were just considering. The second one is the fact that they are inexpensive. Even today, it is often less expensive to do a function with integrated circuits than it is with separate discrete components. The fact that they are small is important. This board here contains many functions, many more functions than we could get in this volume otherwise. Finally, there are new functions which can be achieved with integrated circuits that just plain couldn't be achieved any other way. Harry, we've considered a large variety of topics on this program. I'm wondering if you'd be willing to summarize it for us.
Yes, let's summarize. We started out by telling you what an integrated circuit is. This is an integrated circuit. It's a piece of silicon into which have been built all of the necessary components to perform an electronic function. The piece of silicon in a blow-up picture looks like this. All of the functions are there. We've taken you through the design and building of an integrated circuit, from a circuit diagram through masking to wafer processing, and finally on to the final packaging of an integrated circuit. We've showed you that it takes a lot of extensive testing to prove out an integrated circuit. And finally, you've seen a lot of the uses, both present day and future uses, for integrated circuits. Hopefully, we've given you some ideas on how you can put integrated circuits to work for you.